And so I'll just do one example right now of a stoichiometric calculation with a balanced reaction. So let's say we have this AQ, that is that aqueous state of matter that I was talking about before. It means it's dissolved in water. Actually, I'll make this aqueous, not that it really matters, but as well. See reaction arrow. Just make all of these aqueous for right now, because why not? Except for water, because water can't be aqueous, because aqueous means it's dissolved in water. Okay, so if I want to know how many grams of oxygen are going to react with 1 gram of glucose, which is this C6H12O6. So we have 1 gram of this. And I want to know how many grams of oxygen will react. Well, can you just say, well, if this has a coefficient of 1, this has a coefficient of 6, and I will say, I'm telling you right now, this equation is balanced, unless the problem explicitly tells you that the equation is balanced, you should always double check, right? So unless it actually says, according to the balanced chemical equation, just quickly double check and make sure it is balanced, right? Just for your safety. But this one is, so we can move past that step. So yeah, can you use coefficient and say, there's 1 here, 6 here, so it's going to be 6 grams. Well, if you recall back to chapter 3, you cannot directly relate mass to mass, ever. You have to go, just like we talked about in chapter 3, you have to go mass of component A to moles of component A. Then use the mole-to-mole ratio to go to moles of B, and then you can go back to mass of B. So let's start and do this first conversion. So we've got the mass of component A, which in this case is glucose. So we've got 1 gram. And you have to use the molar mass to go from mass to moles. So remember, think of this as being over 1. So if grams is in the numerator and we want to cancel it out, we have to put in the denominator of our conversion factor grams moles. And the molar mass of glucose is 180. So per 1 mole. So now here I'm going to show grams, the units of grams cancels out, leaves us in just moles, and gets us, for this first step right here, going from mass to moles of component A, we have 0.00555 moles. And again, you don't have to worry too much about sig figs right now, but that is 3 sig figs, which is what we're starting with, because remember, you do not use conversion factors for sig figs. So now we've got those moles, right? So now we can do the mole-to-mole ratio. How do you get the mole-to-mole ratio of a balanced reaction? You get it from the coefficients. Right? So we're talking about glucose and oxygen. So we know that for every 1 mole, so again, what this balanced reaction is saying is that for every 1 mole of glucose that reacts, at the same time, 6 moles of oxygen are reacting with that 1 mole of glucose, so meaning that oxygen reacts 6 times faster than glucose, and that produces 6 moles of carbon dioxide and 6 moles of water. So for every mole of glucose that fully reacts, you get 6 moles of both carbon dioxide and water out as products. Right? In this case, we're just worried about oxygen, so we can do another conversion factor between moles of glucose and moles of oxygen. So this is moles of glucose here. So if we're trying to cancel that out, we can put that in the denominator. Sorry, moles of glucose, moles of O2. So we just use the coefficients from the balanced equation, 6 and 1. Moles of glucose gets canceled out, so now we are in moles of oxygen. That gets us, and as you can see, I'm writing this a little bit differently this time. In the past, I would often write all of the conversion factors together, all in just a single line. This time I wanted to show it differently, where if you do like one at a time, just to kind of reiterate that whichever way you prefer is totally fine with me. As long as you're doing proper math, I don't care which way you set it up. So you can absolutely do one at a time. That's completely fine too. So I've got 0.0333 moles of O2. And now we have to do this last step. Go from moles of component B, which is the oxygen, to its mass. So now we have to use the molar mass of oxygen. Now keep in mind, this is O2. It's not, so on the periodic table, oxygen has an atomic mass of 16, but we need to double that because this is O2. Right? So we actually have 32 grams per 1 mole. And I put mole in the denominator because we need to cancel out units of moles right there. Doing that math, that gets us 1.06 grams of oxygen. And that is an example of a stoichiometric calculation with a balanced reaction.